Megalodon is one of those extinct animals that people think they already understand. Most have seen dramatic images of a giant shark next to a modern boat, jaws wide open, scaled to impossible proportions. But the real scientific story is stronger than the myth because it is grounded in evidence, uncertainty, and ecology. Megalodon, formerly Otodus megalodon, lived roughly between 23 million and 3.58 million years ago, from the early Miocene into the early Pliocene. That timing matters. It was not a dinosaur-era predator and did not share seas with marine reptiles from the Mesozoic. It lived in a world with evolving whales, changing coastlines, and oceans already structured in ways that feel recognizable today. The core question is not whether Megalodon was big. It clearly was. The deeper question is how such a predator functioned for millions of years at the top of marine food webs, and what combination of changes finally pushed it out. To answer that, we have to separate spectacle from data and read the clues left in teeth, vertebrae, habitat patterns, and the broader evolution of ocean ecosystems. A major update in Megalodon research concerns family relationships. For years, popular treatments tied it closely to the modern great white shark, almost as if it were a direct oversized cousin with the same body plan and behavior. More recent classification generally places Megalodon in the extinct family Otodontidae, not as a straightforward member of the same immediate family as great whites. That change sounds technical, but it has real consequences for reconstruction. If Megalodon is not simply a scaled-up great white, then assumptions about shape, movement, and hunting strategy must be retested rather than borrowed. Evolution often produces similar ecological roles through different anatomical pathways. Two apex predators can occupy comparable niches while solving biomechanical problems differently. So this taxonomic shift acts like a warning label: be careful with cinematic certainty. The animal may have shared some convergent traits with modern lamniform sharks, but it likely had its own distinct balance of mass distribution, hydrodynamics, and feeding mechanics. In paleontology, reclassification is not backtracking. It is refinement. As fossil comparisons improve, scientists produce models that are less nostalgic and more evidence-driven, and Megalodon is a perfect case of that process. The most debated subject is size. Depending on method, proposed maximum lengths can range from around 16 meters to more than 24 meters. Those upper-end figures attract attention, but scientists also discuss central tendency, not just extremes. Modal estimates for many individuals across growth stages are often much lower, around 10.5 meters, which is still enormous by modern standards. Why the disagreement? Because we mostly have teeth, plus limited vertebral material, and body length has to be inferred using scaling relationships. If your baseline assumptions about head-to-body proportions or tooth-to-length conversion differ, final estimates shift dramatically. In other words, arguments about size are often arguments about model architecture. The responsible takeaway is this: Megalodon was unquestionably among the largest predatory fish in Earth history, but exact maximum dimensions remain uncertain. That uncertainty is normal with fragmentary fossils and does not weaken the broader ecological conclusion. Even conservative size reconstructions imply a predator with extraordinary energetic demand, high impact per kill, and a feeding strategy centered on large calorie-dense prey. You do not need a single record-breaking number to understand that this animal operated in the top tier of marine predatory power. If teeth are the main fossils, then teeth are our best window into function. Megalodon teeth are thick, robust, and engineered for high mechanical stress. They were not delicate slicing tools. Their architecture suggests forceful penetration, gripping control, and durability under extreme loading, including contact with bone-rich structures. This aligns with bite force reconstructions that can exceed 100,000 newtons and in some models approach roughly 182,200 newtons. Any specific number is a model output, not a direct instrument reading, but the broader implication is consistent. Megalodon could generate catastrophic bite events against very large vertebrates. Functional morphology also hints at feeding style. A predator that can destroy structural integrity quickly has options beyond prolonged pursuit. It can disable key regions, reduce struggle time, and lower injury risk to itself. That matters at giant body sizes where each hunt carries substantial energy costs. You can think of Megalodon's dentition as part weapon, part risk management system. In evolutionary terms, success comes not from dramatic attacks alone, but from repeatable efficiency across thousands of hunting attempts. Robust teeth, high bite potential, and likely strong jaw leveraged together suggest an animal adapted for dependable high-yield predation in a competitive ocean. Hunting behavior is inferred, but not guessed blindly. Compared with modern great whites, which often strike from below and exploit softer regions, Megalodon may have relied more on bluntly overpowering attacks against vital thoracic areas, using massive bite force to damage heart-lung regions and rapidly incapacitate prey. That hypothesis fits the mechanical evidence and the prey spectrum linked to Megalodon fossils, including large marine mammals. At that scale, hunting is a precision physics problem. The predator must approach, accelerate, angle correctly in 3 dimensions, deliver force through moving water, and avoid counter-impact from large prey bodies. Big whales are not passive targets. They can ram, roll, or simply generate escape momentum that punishes miscalculated strikes. So Megalodon's probable strategy likely prioritized fast disablement over prolonged chase. This does not mean it never scavenged or varied tactics. Most large predators are opportunistic to some degree. But over evolutionary time, anatomy tends to mirror dominant successful behavior. Everything from tooth robustness to inferred jaw power suggests that Megalodon's core strategy involved high-impact attacks optimized for large prey handling. It was not merely oversized. It was specialized for a specific level of predatory challenge. Distribution patterns indicate Megalodon had a cosmopolitan marine range, appearing across many ocean regions rather than one isolated basin. But global range does not mean uniform lifestyle. One of the most important ideas is ontogenetic habitat partitioning. Juveniles and adults likely used different environments. Younger megalodons appear linked to warm coastal waters that functioned as nurseries, offering food availability and relative safety while body size and hunting capacity developed. Juveniles likely fed on fish and smaller cetaceans before transitioning toward larger marine mammals with maturity. This life cycle structure is crucial for understanding both dominance and vulnerability. A giant apex predator is sustained not just by adult success offshore, but by repeated juvenile recruitment in suitable nursery habitats. If those nursery zones contract or fragment, population renewal weakens even if some adults still survive. That makes coastal geography, temperature gradients, and sea level dynamics central to Megalodon's long-term viability. In modern shark conservation, nursery integrity is a core principle. Deep-time evidence suggests the same logic applied to Megalodon. So when we map where fossils occur, we are not simply plotting points. We are reconstructing an organism's full life cycle architecture across dynamic marine landscapes. Megalodon's ecological impact likely extended beyond direct kills. Apex predators shape ecosystems through both consumption and fear effects. If large marine mammals alter migration routes, feeding locations, or group behavior under predation pressure, those shifts can influence nutrient transport and food web structure over broad scales. A predator of Megalodon's probable size and distribution could have imposed persistent risk landscapes in many regions. Potential prey included whales, seals, and sea turtles, with large whales representing especially valuable energy targets. That prey profile places Megalodon high in trophic hierarchy, interacting with species that themselves influence lower levels of marine ecology. In other words, Megalodon was not just another shark, it was likely a structural actor in ocean community dynamics. This perspective helps explain why extinction of top predators can produce cascading effects. Remove a dominant hunter and you do not simply subtract one species, you alter behavior networks, competition balances, and resource flows. While precise cascade details are hard to reconstruct millions of years later, the principle is robust. Megalodon probably mattered because of where it sat in the system, wide-ranging, high-energy, and connected to major marine mammal pathways across multiple ocean provinces. Even top predators face competition, and Megalodon's oceans included other formidable hunters. Macroraptorial sperm whales such as Livyatan and related large cetacean predators occupied overlapping predatory space in parts of time and geography. Competition does not require identical menus every day. Partial overlap in high-value prey can still create pressure, especially when environments fluctuate. There is also discussion of ancestral or sinus lineages, though likely with variable diets, and some early forms may have focused more on fish and cephalopods than giant mammals. The key point is ecological crowding at upper trophic levels. When multiple large predators depend on energetically rich prey, system shocks, temperature shifts, prey redistribution, habitat loss, can amplify conflict and reduce margins for error. For a giant shark with high metabolic demands, reduced prey reliability is costly. Competition then becomes less about dramatic one-on-one encounters and more about chronic energetic arithmetic, who can find enough food efficiently, across enough generations, under changing conditions. Megalodon's long duration shows it succeeded in that arithmetic for millions of years. But long success can hide underlying sensitivity when system parameters move outside historical ranges. Climate and oceanographic change likely supplied the decisive pressures in Megalodon's decline. As global cooling advanced toward Ice Age conditions, warm water habitats contracted and ocean circulation patterns shifted. If Megalodon preferred warmer zones, this would have narrowed suitable hunting and breeding ranges. Simultaneously, sea level drops reconfigured continental shelves, potentially reducing or fragmenting shallow coastal nurseries needed by juveniles. Population resilience depends heavily on juvenile survival. Damage that stage and long-term decline can unfold even with surviving adults. Prey dynamics were also changing. If baleen whale diversity decreased regionally or migratory behavior shifted toward higher latitude colder waters, Megalodon may have faced a growing mismatch between thermal preference and prey access. A massive predator with high daily energy demand cannot easily tolerate persistent prey instability. Add competition from other large marine hunters, and pressure compounds. Importantly, extinction here is unlikely to be a sudden event. It is better modeled as gradual demographic attrition, reduced recruitment, patchier prey fields, narrower habitat windows, and cumulative energetic stress. Over enough generations, that combination can push even a dominant apex lineage beyond recovery thresholds. An intriguing context is that Megalodon's disappearance overlaps with trends in baleen whale gigantism. As some whale lineages became larger and possibly altered migratory ecology, predator-prey mechanics may have shifted against Megalodon, especially if suitable attack opportunities became less frequent in warm regions. Larger prey can be rewarding, but also more dangerous and less predictable, particularly when predator populations are already stressed by environmental change. This interaction highlights a broader evolutionary rule: adaptations are conditional advantages. Megalodon's massive body, powerful bite, and likely large prey specialization were extraordinary strengths in one ocean regime. In another regime, those same traits may have become less flexible. Specialists often dominate stable or favorable systems, then struggle when multiple variables change simultaneously. Megalodon's end, therefore, is not a simple story of one competitor defeating another. It is a systems transition where climate, habitat geometry, prey movement, and trophic competition all reweighted the survival equation. That makes Megalodon scientifically valuable beyond its size. It serves as a case study in how apex success can persist for millions of years and still unravel when ecological foundations shift faster than adaptation can keep pace. What remains today is a paradox. Megalodon is globally famous, yet still partly mysterious. We have enough evidence to be confident about its identity as a giant, high-impact marine predator, but not enough to resolve every anatomical detail with certainty. That tension is exactly what makes the species so instructive. It demonstrates how science works with imperfect records, building convergent conclusions from independent clues while keeping uncertainty explicit. The strongest conclusions are ecological. Megalodon occupied apex roles across broad ocean regions, depended on large prey networks, likely used warm coastal nurseries for early life, and declined as climate cooling and ecosystem restructuring reduced those supports. Instead of treating Megalodon as a fantasy monster, we can read it as a real evolutionary narrative about opportunity, specialization, and limits. In modern terms, it also offers perspective on present oceans, where top predators again face rapid environmental change. The lesson is not that history repeats exactly, but that ecological power never guarantees permanence. Megalodon ruled for millions of years, then vanished. Its story is a reminder that in Earth systems, dominance is temporary, adaptation is conditional, and the ocean is always rewriting the rules. If you found this helpful, please like this video and subscribe for more explainers.